What we've learned is that sometimes certain types of nuclei will spontaneously emit some of the nucleons inside of it, which will go flying off at a really, really high kinetic energy. And this causes the original parent nucleus, which was radium-226, to turn into something totally different. And this process is kind of strange because what it means is that somehow the nuclear force, which is really, really strong, temporarily lets go of some of its nucleons, causing them to go flying off at tremendously high speeds. Now, this process of the nucleus, or the nuclear force, letting go of some of its protons and neutrons is a little hard to understand, and it's explained using something called quantum tunneling. Quantum tunneling is beyond the level of this course, so we're not going to study it, but you can imagine it like this. If we take an electron and we put it inside a box with infinitely high walls, so these walls go on forever, and here's the electron at the bottom. Clearly, the electron can't possibly have enough energy to go up and then come back down to land outside on the floor. That seems impossible, and in fact, it won't happen. However, if we take the same electron, and instead of placing it inside of a well or walls that are located right on the ground, let's say that this well is elevated a little bit above the ground, and so the ground is down here, and this thing is being suspended maybe by a rod. Well, again, we might think that because these walls go on forever, there's no way for the electron to possibly get out here. It doesn't have enough energy. In fact, because of something called quantum tunneling, there is a way for the electron to tunnel from its position here to a lower energy state. The electron, we say, has tunneled down to a lower energy state. And the same kind of thing can happen with nucleons when they tunnel out from the nucleus. And that's how an alpha particle can be ejected from the nucleus. Now, because this is a quantum effect, it is probabilistic by nature. What that means, if we have just one single atom, we have no idea and cannot predict when exactly this one atom is going to decay and when its alpha particle will quantum tunnel. We can't describe it because quantum mechanics is only able to discuss things in terms of probabilities. So really what we can say is there's a probability of this thing decaying in a certain amount of time. Now, this is no different from saying that if we flip a coin just one time, we have no idea of guessing whether it'll be heads or tails. But we do know that if we take 5 million coins and flip them all at the same time, roughly 1/2, or 2,500,000, will be heads, and the other 2,500,000 will be tails. And this won't really be a guess. We'll find that these estimates are extremely accurate if we flip this many coins. And just in the same way, if we take not just a single nucleus, but 5 million nuclei, we can very, very accurately predict how long it'll take for exactly half to decay. So instead of dealing with just one, we are going to take this one nucleus, like this, and zoom out our picture, so that instead of just dealing with one, now let's say we have another one here, and another one here, and we keep adding the same nucleus like this until we have 5 million nuclei. And remember that each one of these little black dots, if we put it under a magnifying glass, it would look like the original nucleus with lots of protons and lots of neutrons. So as time passes, every now and then, one of these will eject an alpha particle. And that means as each time an alpha particle is ejected, one of these nuclei will change into something totally different. And I'll represent that with a green dot. So now this one has changed, and maybe this one here has changed, and this one here has changed. Right? And so what we can do is, as time passes, oops, I forgot this one down here. As time passes, we can count how many of the original nuclei, the black dots, remain. Let's say that for this particular sample, which I'll just call substance X, okay, for substance X, after 4 seconds passes, so now we're 4 seconds later, we only have 1/2 of the original amount of nuclei, and the other half have all changed into something new, maybe substance Y, upon ejecting some alpha particle. Believe it or not, even though we are not able to say exactly when any one of these black nuclei will decay into a green nuclei, we can say that if it took 4 seconds for half of this huge sample here to decay, then in general, it will always take 4 seconds for half of a huge sample to decay. So this number, 4 seconds, the amount of time for 1/2 of a sample to decay, is called the half-life. And it's one of the ways we measure how radioactive a substance is and how often or likely it is to decay. So let's say we want to make a graph, and on this graph we are going to track substance X over time. So the x-axis is time, and what we're going to track specifically is how many nuclei are left in the substance. So we start with some giant ball of substance X, some big sample. So here's my big sample of substance X, and at time 0, when the clock is at 0, and I haven't started time yet, at time equal to 0, that's right here, let's say we have 1 million nuclei in my sample here, right down here. There's a million. And of course, after 4 seconds for substance X, so we put a dot right here. So after 4 seconds has passed, we know that half of this sample has decayed because the half-life is 4 seconds. So instead of having the original amount, now we have only half of the original amount. And we can even do an experiment where we count how many are left, and we see that, yes, half are gone. So after 4 seconds, we need to put a data point right here. And this, on the y-axis, is half of a million, or 500,000. Now, we wait another 4 seconds more so that we are at a total of 8 seconds, right? And I'm not sure what kind of clock I'm using because that's not 8 seconds, that's for sure. But we wait, and after 8 seconds, another half of the remaining sample, so half of this sample that we had, has gone away. And so what we have left is half of what there was. We have half of 500,000 left, which means we're another halfway to the x-axis, and that gives us 250,000. So that's how many we have here at 8 seconds. And after 4 more seconds, right, now we have half of this amount remaining. So instead of having 250,000, now we have half of that, and again, we have gone halfway down the x-axis to 125,000. And so we need a data point here. And if we keep drawing the curve like this, what we see is it does something like this. It curves down to the x-axis, and it approaches the x-axis, but never actually touches it. And I haven't done a very good job of drawing my curve because it should be passing through the data points. So this kind of curve is called an exponential decay. Exponential decay. And half-life is a great example of exponential decay. So here's a question. How much of a sample of 1,000 grams of substance X will remain after 16 seconds? And it says here, the half-life for substance X is 4 seconds. So here's how we approach this problem. We say that at time 0, the amount we have, is 1,000 grams. And we could measure this in grams or moles or number of nuclei. Any measure of the amount is suitable. And grams is one measure of amount. So after one half-life, that's 4 seconds, we'll have lost half of the original sample. After another half-life at t is 8 seconds, we will have lost half of that sample, half of 500. And after another 5 seconds, after another 4 seconds rather, when we have reached a time of 12 seconds, how much will be left? Half of 250, which is 125 grams. And we keep going like this until we reach the amount of time they've given us, which is 16 seconds. So after another 4 seconds, we'll lose half of 125, which is 62.5 grams, and that's our answer. So how much will remain after 16 seconds? 62.5 grams. Another interesting question that we could have been asked is how much of substance X will have decayed after 16 seconds? And if they were asking for the amount that had decayed, well, we would find this number, 62.5, and then we would subtract it from the original amount to see how much had decayed. And the answer to that question would have been 937.5 grams. Now, what we've been doing so far is we've been counting how many nuclei there are after some amount of time. So after maybe no seconds at the very beginning, we have 100,000. And then if we wait for one half-life, we have half of that, 500. Let's see, what did I say? 100,000, so we would have 50,000. And then after another half-life, we count the nuclei, and we have even less, right? 25,000. And we continue moving down like this, 12,500, counting nuclei after each half-life has occurred. So one way to measure the radioactivity of a substance is to just count the nuclei. How many nuclei are there after some time? But there's another important way, which we'll quickly look at next. Besides counting nuclei, another way we can measure how radioactive a substance is using something called radioactivity. And we can think of it as activity. We can think of it as the activity of the substance, or how many nuclei it ejects in 1 second. So if we take some substance and we watch in 1 second how many nuclei are decayed and eject an alpha particle, like this. And in 1 second, we count the number of alpha particles that are ejected, we count the activity. The radioactivity is the count that we get, the number, per second. So initially, right, let's say that in the very first second, how many do we count? The radioactivity, what is it? Let's say we count 1,000 nuclei that decay in the first second. Now, we wait 4 seconds, or let's make it longer. Let's say we wait 25 seconds. And after 25 seconds, we have a smaller nucleus here because we have a smaller sample because some amount has decayed. And then, after waiting some amount of time, now we take another count and we say, what's the activity at this point? What's the radioactivity? And after having waited a little time, there are fewer nuclei, and so there are fewer being ejected from our sample. And so at this point, maybe the count per second is 750 per second. And as it turns out, this type of way of measuring the radioactivity also follows an exponential curve. But before we get there, we have to understand what the unit is for the activity. If we look at the numbers we've written in, clearly the unit is 1 over a second. In the numerator, we just have the number of counts, the number that we count. In the denominator, we have 1 second, because that's how long we counted for. And 1 over a second, you might think, is a hertz, but when we're dealing with radioactivity, we have another unit we use instead, called the becquerel, named after Henry Becquerel, who, with Marie Curie, discovered radioactivity. And the becquerel is given the symbol BQ. So here, instead of 1,000 per second, what we could write is 1,000 becquerel. And down here, we could have written 750 becquerel. So now we have two different ways to measure activity, or how radioactive a substance is. One way is to just count nuclei that remain. And what we said is when we do this, the number remaining against time creates this exponential decay curve, which approaches but never actually touches 0. The other way now that we can measure how radioactive a substance is using what we just described, count radioactivity, count nuclei that remain. And the other way we've just said is we can count the number per second that are decaying in the sample. And we call that the activity measured in becquerel. And as it turns out, as a substance decays, it becomes less active. So fewer nuclei will be decaying as less and less substance exists. So as it turns out, believe it or not, we also get this same exponential decay. And the reason that this happens is because the number of nuclei that remains is directly proportional to the activity. And that is an important fact which we will be using in some of our problem solving.